A little bit of background to what we're going to be doing here today. We want to give a little bit of history of what we've discovered in the 3.5 years we've been doing LMAX. And we're going to finish off with the new concurrency pattern that we're putting forward at the moment. And it kind of goes against all the modern trends. So we're kind of looking forward to sort of people throwing sort of rotten fruit at us, whatever you want. LMAX, London Multi-Asset Exchange. Dan's done a good job of introducing us. We're a financial exchange. We're different from most other financial exchanges because we're going to be open to retail, in that you or I can go and trade on this exchange without going through a broker. It's like where anywhere else you've got to go through layers and layers to get there. That's going to be our proposition in taking out the middleman from how we're going to make our money. But what makes that really quite interesting for us is we've got two problems of scale. One being exchanges have to go incredibly fast, but they normally only deal with a small number of concurrent users. Because we're opening this up to the internet, we compound our problem by having very large span out of concurrent users, plus incredible throughput, and we'll get around to in a second, a great deal of contended concurrency. Okay, we're a spin-off from a company called Betfair, which over here you may not have heard of. In Europe, they're fairly well known because they're the world's largest sports betting exchange. They do futures on sports. And this little internet company, it processes more trades per day than all the European stock exchanges combined. Pretty serious volumes. And what makes it even more difficult is you normally get a spread across most of the instruments that are busy. So like at any given time, people are trading Google, they're trading Apple, they're trading Microsoft. You can spread that problem out. Because it's sport, sports are not scheduled to conflict with each other, so you get a massive concurrency problem. It's always the World Cup final, the biggest horse race. And even within that, it'll be one side is favored more than another. So as a problem, we just can't take this and put it on lots and lots of machines. We have to work out how do we do this at transaction volumes that there's only a handful of sites in the world see, but we've got to go on the same data.
One of the next things to talk about is how we differ. There's a lot of similarity between a financial exchange and a betting exchange. It was sort of a kind of a joke that the natural progression from gambling is straight into finance. But one of the key differences, we have a little bit of, we're slightly eased in the fact that we do possibly can partition out across different instruments. A bit later we'll talk about why we actually don't bother doing that. But the key difference is latency. With betting, and especially over the internet, you can handle 10 milliseconds, 100 milliseconds, 600 milliseconds latency between placing a bet and getting a response. You know, with financial trading, with the market moving very, very quickly, like some of the FX markets, they're extraordinarily volatile. Our wholesale market makers don't want to see very long latencies because it basically introduces risk into their systems. When you introduce risk, they widen their spreads and they give a very, very poor experience for our retail customers. Sorry. Okay. So yeah, it's lost what I was talking about. So yeah, it's largely about there's a really strong financial benefit to us to reducing the latency for our market makers because it provides us a much better product for our retail customers.
Yeah. It's key to the business model. The lower the latency, the better the reinforcing cycle for us. But even more important than low latency is very predictable latency. Market makers will trade a little bit of latency as long as it's extremely predictable. And we're talking in the order of microseconds to milliseconds at absolute maximum. So how do you solve this problem? There's a number of ways you can tackle it. You could try a big database. It's actually what Betfair did originally. And they have the third hottest Oracle database in the world and the most contended Oracle database in the world. It's so bent out of shape you wouldn't believe to do amazing things. But it's really the wrong solution to it. And even at that, you can't get the volumes that we need or anywhere near the latency requirements we need.
Another possible solution is J2EE. It's just really a way of doing RDBMS in Java. At the end of the day, it just basically gives you transactions and stuff. And it wasn't so much saying J2EE is really bad, it just J2EE doesn't really buy you anything. It doesn't really give you any extra assistance in this space.
Now, we've done a lot of research into this. I come from originally from Bedford, where we try to solve this problem. We kicked off a project called 100X. The goal for the 100X project was to come up with a new exchange to design that was 100 times the scalability of the current system. And remember, that current system, more throughput than all the European stock exchanges combined. So we looked at lots of architectures. One of them we looked at and actually built a full prototype in was SEDA, Stage Event-Driven Architecture. It's quite interesting. It's also quite similar to how some things are happening with Actor and Erlang and different things at the moment. But what we discovered in this, trying to work out which thread something should run on, where things should be queued, there was so much red tape and bureaucracy going on inside the architecture, you weren't actually getting real work done when you get to these volumes. It's fine on smaller volumes, but when you start getting to serious volumes, it doesn't work either.
The other model is the Actor model, very, very similar in a lot of ways to SEDA. SEDA tends to be sort of a one-to-one mapping of objects to threads. Actors are sort of an end-to-end model, but you tend to run into the same problems you run into with SEDA. When you get it to extremely large volumes, you end up with the latency spikes because you're queued, you get pushed off the thread, you get some sort of other blocking operation might jump in on the thread in front of your piece of business logic. So it's hard to build a really, really low latency, predictable solution with SEDA and the Actor pattern.
Yeah, and this is where we're going to be controversial. We're going to propose that queues are actually completely the wrong data structure for doing any sort of messaging between two different components. And I'll get into why on a modern CPU. You could try flavor at the moment. Nah. 2 seconds latency at the best case. The pattern we're going to propose, we've nicknamed it internally Disruptor. Why Disruptor? First off, it's got elements that are quite like phasers, which are coming in JDK 7. It's a little bit more specialized than that, but the other main reason is we actually want to disrupt current thinking and how some of this stuff is done.
Okay, first off, we're going to just pass out some general tips. These are the sorts of things we've run into when we've tried to build high performance, low latency, high throughput systems. And it boils down to some fairly simple constructs. Simple code, well-modeled domains, and a thing that Martin likes to call mechanical sympathy, which is just sort of understanding what's going on under the covers.
All right. So let's kick off with a bit of mechanical sympathy. I'm going to talk about what are the 4 basic building blocks that most computing is based on today. First up, memory. What's been happening over the last 10 years in particular has really changed the game. We've been working a certain way, and then the game has changed, and most people haven't actually realized that latency to memory hasn't dramatically improved now for over a decade. And it's fundamentally how the charge cycle works in DRAM, and it's not going to get much faster. Bandwidth is going up phenomenally to that memory, but the latency is still there, and you can't really avoid it. Also, there's so much memory you can get in a commodity machine. You can spend less than $3,000 now and get a machine with 144 gigabytes of RAM in it. You can spend a few tens of thousands of dollars and get a machine that's up to a terabyte of RAM. The other thing that's interesting is CPUs. Everybody's heard the gigahertz race is over. And we're saying CPUs are not getting faster. It's not true. CPUs are getting faster. They're just getting faster in different ways. In particular, the caches have become much larger and much smarter. So to understand how to get the best out of CPUs these days, you've got to understand how caches work. And core counts going up. So how can we make use of those cores? Networks. Everyone says networks are slow. Not really true when you start looking at what's happening with 10 gig E. 10 gig E now has a feature called RDMA built into the standard, which lets you even bypass the kernel. You can go from user space in one machine to user space in another machine now in sub 10 microseconds with this correctly set up. That's a game changer for some of the things that are going on. Most people aren't even aware this is possible. You can go down to things like InfiniBand and get even lower, but that's getting a little bit proprietary. Just sticking with standard 10 gigabit Ethernet is very good. And even on single gigabit Ethernet with things well set up, particularly if you use UDP or multicast, you can get very good low latencies and very good throughput on these machines. And kind of last area I want to cover is storage. People sort of keep using disks as random access. Disks are not random access. You only get about 100 IOPS a second per given disk from a seek time. But what's actually interesting about disks is they have got amazing sequential access, and that's been driven by multimedia. If anybody's been around this game a while, about 15 years ago, you had to buy special disks from multimedia. It's now just standard. They're amazingly good at streaming, incredibly reliably, incredibly fast. So you can think of disk is now the new tape. If you want to do random access, use SSDs. Terrible name, there's no disk inside them. They're just solid storage, but very good for random access, particularly for many threads hitting a random pattern. One thing that was interesting for us is that per single thread, they're not actually that fast, not much faster than a normal disk if you're dealing sequentially. It's great when you throw lots and lots of threads at them, but not for single threads. And one of the fundamental limitations with SSD-based technology is they've got a disk controller interface on the front of them, and that's fundamentally limited. So there's lots of new things coming out where you're getting directly PCIe directly connected infrastructure that goes significantly faster. And here's one example, like HDS storage array. I sort of worked in a company that had 13 of these, very, very large. That little card on the right-hand side of it can fit in a standard PC. It's a Fusion I/O card, and it can do the same number of IOPS as that wardrobe next to it. It's significantly more expensive.
Keep the working set memory. This is kind of an interesting one. My boss, Dan, talked about recently, has a really great saying that working with a database, working with tools, even like tools like Hibernate and various caching tools that make things a bit easier, it's still like trying to eat your dinner through a letterbox with a pair of chopsticks. You know, when you take and put your entire model into memory, your whole perception of things changes. You start working in terms of, your computer science 101 things. You're modeling your relationships in terms of collections. Is it a list? Is it an index-based access? Is it a sort of a sequential access, so I need a sorted tree? And it's a really, really important aspect to what we're doing, and actually makes a lot of our code much, much cleaner. One of the key game changers that has allowed this sort of thing is 64-bit addressing. And previously, when you're stuck with 32-bit addressing, you're stuck with roughly 4 gigabyte heaps, and you couldn't go beyond that. But now with 64 gigabyte addressing, you can address hundreds of gigabytes of RAM. You talk to the Azul guys, and they'll basically give you a JVM that will take up the entire machine and won't pause. So.
Let's dig deep for a second. So this is a CPU architecture from an Intel Nehalem. It's quite an old one now. You took in a Nehalem EP at this stage, so 4 cores per socket. What I want to cover a bit is how memory works in this sort of architecture. And so down at the bottom, we have got all of our cores. If you're on 32-bit, you've only got a handful of registers to play with. It's not very exciting. 64-bit is a game changer in many ways. There's 128 integer registers and 128 floating point registers at your disposal. So all your local variables can be in a lot of that. Going up from that, when you're doing all your operations, you have to do them on the registers themselves. So how do you feed the data into that? Well, you're feeding data in hierarchically. And so the nearest thing is the level 1 cache. The level 1 cache is 64K. It's split 32K instruction, 32K data, and how it works. So keep a nice, clean, compact code. That sits nicely in that 32K cache. And the data that you're going to be working on directly is typically in the L1. It's staged through the L2 cache, which is typically 256 going out. And that's where you access the main L3 cache. So everything's always right through in these scenarios. L3 caches now are anywhere between 8 and 24 megabytes, which is really significant, and they're very fast. But you notice that it's going out, and it's getting longer and longer in latency to access this. The thing about the caches on chip, you don't measure them in time, you measure them in cycles, because they're using SRAM, and SRAM is cycle-based rather than having that charge cycle you get with the DRAM that's further out. So as CPUs get faster, your caches are faster as well. The interesting thing is the L3 cache, from a concurrency perspective, is where you share data. So if you can get data flowing between cores through L3 caches, that's how you get a lot of performance. What's important about the caches and getting out to the DRAM at the other end is data is not fetched from memory a word at a time. A lot of people think this. It's fetched in cache lines, and that's for efficiency. On this sort of CPU, a cache line is 64 bytes. So things that are co-located, you end up getting pulled in together. And that's really useful for when you're designing stuff, so you understand how these things work. You can make things go much faster. So a typical object and all its headers will come in one cache line. Where you've got to watch out for is when you're doing concurrency. If you've got two things that are hot, you want to make sure they're not in the same cache line. Otherwise, you've got a contention problem. The cache lines are pinging between the cores all of the time. You want them just always to flow in one direction. So an ideal world is any piece of data is owned for write by a particular core. Just think on a macro level. We're just taking this down now to a micro level. You don't want multiple services all writing the same piece of data and they're agreeing between each other who should own this piece of data. It's exactly the same on a micro level. Have a core own a piece of data and make sure it's the only thing that updates it. And then it can broadcast it out, many copies of it elsewhere for other things to read. Also, modern CPUs are now NUMA, they're non-uniform in how they access their main memory out in the DRAM banks. And so you have to pop across either the hypertransport if you're on AMD or the quick path link if you're on Intel. These links don't actually add that much overhead. You're talking in the order of sort of 18 to 20 nanoseconds to hop across these links. They become very, very fast. You go back to previous memory architectures, it was actually much slower through the normal memory controller out to DRAM, so the links actually don't matter that much. What's really neat about the Intel chip is the memory controller on the other side, when you go to access that memory, it fires a request into the cache and out to DRAM, and the first one to respond, it sends back. So that's really nice if it's hot in the cache on the other side. So everything's flowing very fast through all of these caches. And it's the thing to watch out for when you're doing high-performance computing. It's not just this chip, and this is what I'm saying about the mechanical sympathy. You've got to know what you're working with. If anybody programmed games in the 80s and 90s, you had to know how your CPU worked to get the best out of them. CPUs have got phenomenally fast. And if you understand how they work, you can get a lot out of them.
Just going, one more point on this one is that in a modern CPU, if you take away any form of I/O, the most expensive operation is going here. That's why our cache misses are an incredible hit. So it's an important consideration to bring in when you're writing fast code is that try and think a little bit about the cache locality of your things. If you are dealing with something like a linked list versus an array, a linked list you're going to traverse pointers all over your memory. So you've got a much, much higher chance of ending up with a cache miss and forcing one of these very, very slow operations. And it tends to be in a zigzag pattern, so the CPU can't do anything about your access pattern into memory. You're running through an array, it's pulling these things in a cache line at a time, so it's pulling in multiple entries of that array at the same time. And also modern CPUs can actually see sequential access patterns and start prefetching, getting that data hot into cache as you're going. So it's very, very important when you're thinking about writing fast code.
Yeah. So the point Mike made, there's CPUs do a modern thing called striding through memory. So if they see a predictable stride, they can actually prefetch that so it's pipelined and ready for you. This is where writing nice code that's predictable through memory rather than randomly going everywhere goes much, much faster. And you'll see a theme coming out here. Simple code works much better.
Write clean, compact code. Astounding piece of information. Quote from Einstein there, any intelligent fool can make something bigger, more complex and more violent. It takes a touch of genius and a lot of courage to move in the other direction. And this is probably one of our fundamental tenets where we work. And admittedly, we don't always follow it. We work very, very hard to try and keep things small and compact. One of the best thoughts, if you're thinking about writing fast code and you're trying to optimize something, put yourself in the shoes of something like Hotspot or the C compiler or whatever compilation technology you happen to be using. And think about the work that they have to do to make your code nice and clean and well optimized. If it's small, if it's simple, it's going to have a much, much easier job. It's going to inline things much, much cleaner, and it's going to allow that code to run really quick. So it's a very important thing. Just small, simple code, single responsibilities.
I can give one real example of this recently. We had a piece of code and someone came up to me and said, try-catch blocks are really, really expensive. Don't do them. Let's remove them from the code. And we actually went through it, and I proved with the micro benchmark, it's not actually that expensive. What had happened was there was a method that had grown to be so complex, it tripped over a threshold where Hotspot just gave up on it. And that's where it's not so much these things and it becomes folklore that people do. It's just get things simple. If you get things simple, none of these primitives are expensive.
And just to build on that one, we actually looked at, we ripped out just this try-catch block, and the performance of this particular piece of code went up by an order of magnitude. And it's probably just because that method was so complex you couldn't be pulled in or inlined into another method that really needed to be hot and local.
Modeling. I cannot believe that modeling is the only thing in what we do, yet so few people seem to do it. The rest is just typing. If you're building anything, sort of go back to the fundamentals of OO is create a software simulation of the domain you're dealing with, and that applies at the hardware level or at the business level. So if you want to write something that drives a disk controller really fast, you've got to have a model of how a disk controller works and drive it that way. You need a model of your business to drive it that way. And if the model is correct and you implement just the model, by definition, you get high performance, simple code because you're not doing anything other than what you actually need. It's not about doing loads of really, really clever bit shifting and doing all sorts of obscure code. I take people through this all the time, and so they're always shocked when they see what is high-performance code. They go, well, that's just simple. Exactly. That is why it's high performance. So getting your models right are so important. And one of, I think, the most important things I've seen over and over again is where it breaks down is the single responsibility principle. When people break this, and I go around ranting at times going one class, one thing, one method, one thing, one statement, one thing. Because as soon as you start conflating concerns into something, the complexity goes up. Combinatorial is the product of the concerns you put inside something. It's not a linear thing. It gets really very complex very quickly. So separating concerns out from classes is a big win, just from reading and understanding the code as well as getting it to be high performance. And it's also really important to understand the relationships in your model. Most people draw a line. Drawing a line is not really good enough when you want to understand how it's going to be used. What is the cardinality? What is the methods by which that relationship gets walked? What are some of the characteristics you need of it? It's important to go over these things in a model and making sure whatever you've done for implementing a relationship makes sense for the cardinality and the usage pattern.
Taking the right approach to concurrency. This is an interesting one. There's really two key aspects to concurrency. One is the mutual exclusion side of things, making sure two things don't access the same piece of data in a way that becomes unpredictable, that sort of thing. The second principle, which is one that people generally tend to forget, and it's the least understood, and it's probably the cause of more concurrency bugs than the mutual exclusion side of things, and that's visibility of changes. When you think back slightly to that particular model we were looking at previously with the model of the CPU, if something's in the L3 cache and it's been modified, and then your code happens to run on a core that's not sharing the same L3 cache over on a separate socket, that's not visible. It's not actually written back to main memory until the CPU decides or the program decides that it really needs to do that. So it's often it's a much more subtle problem when you come to concurrency. And there's kind of two sort of approaches that seem have come through. Locking concurrency, which is probably most people are familiar with, sort of standard synchronized blocks inside of Java. The other is the non-blocking side of things. This locking stuff is kind of tricky. You do kind of need to know what you're doing, but it's not the worst thing in the world. The atomic non-blocking stuff is a bit harder. You really do have to think very carefully about visibility when you're working with non-blocking algorithms. Who here has used atomic and CAS operations, understands how they work?
That's two questions. Yes.
That's two questions. Does anybody know how they work? Who here has done optimistic locking in a database? You've done non-blocking concurrency. It's basically the same sort of principle. The idea that you have something, there's sort of an aversion associated with it, and you simply, when you write it back, it checks to see that whether that version is correct. If it's fake, if something's changed in the meantime, it will give you a response. It actually returns a boolean to tell you something it's not quite correct. The really interesting thing about the atomic and CAS side of things is this is really well optimized by the CPU. This actually boils down to sets of actual machine instructions. On the Intel CPU, things like XAdd, you can atomically increment an integer. One of my big beasts when the first time somebody introduces concurrent code in any programming language, I even see the Google guys do this with Go. I said, right, first thing I'm going to do is teach you how to write a shared incrementing integer. Lock, increment, unlock. There is a single machine instruction. If you use atomic and CAS type operations, you can actually do that in a single machine instruction, rather than a huge number of instructions required to actually lock that variable. The worst case, if you're using locks and you have two threads come into the same variable at the same time, it is quite possibly one of the worst things you can do, because at that point, both of those threads have got to go all the way down to the underlying operating system. And this is if you're using virtualization is important, because it's not just the virtual kernel, it's the lower OS kernel. So you go through all those layers and get the kernel to arbitrate between those two things. This atomic has stuff, it all stays in user space. So it's one of the things when somebody shows you the best way to write an atomic, an incrementing integer, which is shared between threads, it's actually the wrong approach. And my concern is it leads people towards thinking the wrong way about concurrency. And this becomes very important. We can talk about a bit of this later.
Yeah. And why do you think a lock is a problem in a system that you're trying to get into almost real-time characteristics? Well, the problem is when you're on a general-purpose operating system and you go to the kernel to arbitrate your lock, it's taking your quantum away. And once it's taken it away, it might actually decide, do you know what, I'm going to defragment a piece of memory, or I'm going to do some other general housekeeping in the background. When you get scheduled to run again, it could be at any random time. And even worse, you could be running on another core. And that nice hot cache that you had from before is now gone because you're elsewhere. So the interesting thing here is, well, let's just take all the concurrency out, and what can we achieve on a single thread, on a single core at the moment? Well, you've got about 3 billion instructions a second to play with on a single core if you've got a 3 gigahertz chip. Actually, what's interesting is most of those CPUs have usually got multiple execution units inside them. You've got a couple of shifting units, you've got an LU, you've got load and stores, and those things can all happen in parallel. So you might actually have way more instructions in the 3 billion that's going on. And things like hyperthreading are actually implemented by, if something needs a different execution unit from another, it can run and go ahead anyway. So it just keeps pipelines for all of this stuff. So this is a lot of instructions to play with. It's very easy to get 10,000 plus transactions a second in this sort of scenario. Just don't do anything stupid, really. But what if you write pretty neat, clean code? It's very easy to go up into the hundreds of thousands of transactions a second. If you want to start getting really funky and you want to write custom collections, it's one of the things we've done is we've replaced most of the JDK collections with very cache-friendly ones with our own implementation. They don't generate any garbage. We model very carefully how we create garbage and control it. We're also very careful about all the relationships and getting our domain model just right. It's possible to go into millions of transactions per second. When we redeveloped our core exchange, and our exchange is more complex than other exchanges because the retail features, we allow complex order types to execute inside the exchange, not just simple order types, and carry customer positions with those. We could get up to 6 million orders a second through that core matching engine and how it works. The hardest thing I found with most of this for people getting their heads around it is you need to do test-first development, particularly for performance. A lot of people develop stuff and then later try to optimize it, and that's what we're all told to do. Don't do premature optimization. That's completely fine when you're doing true optimization. It's different from actually writing tests to assert the performance that you should get, and you start with those. I spent most of the 90s fixing performance issues in systems, made a good living out of it, and the thing I found more common than that was not the target code being the problem, is people's performance tests were often the bottleneck. And it still keeps happening over and over again. So write the test first, write them against a blank, and make sure that works right, then write against the object code that you're going to target.
We even made this mistake. Actually, just sort of during this conference, I've been busily changing the way that we actually run our performance tests and assessing the performance. One of the things we ran into, especially when you start getting up to high volumes, you've got to separate your load generation from your measurement. You know, we were running into, we're getting some strange figures outside of our performance test, especially when we're trying to push right up to this 100K a second. Our latencies are increasing, and we're looking through the actual test code, and really realizing there's quite a bit of complexity. There's quite a bit of extra code in between when we send the message out and when we timestamp it when it comes back. And we needed to effectively eliminate that, because there's a GC pause in the thing that's sending it out, and you're trying to measure 4 nines on your latency. If there's a GC pause in your load testing tool and measuring tool, what's going to happen? You're going to get very, very strange results. So it's a key thing. Also, separate load from measurement is one of the more useful things we've discovered. Right. We've got this really nice well-modeled domain. We've got this elegant single-threaded model. We've got our custom cache-friendly connections. We're doing 1 million transactions a second, and all it really gives us is a really hot CPU. So you've got all the enterprise constraints as well. So this is where your business wants a system that you can switch off on and off again occasionally, replicate over to a buddy, so if one fails, you've got another one there, have a DR site, all those sorts of things. So unfortunately, we start with this nice single-threaded thing, but unfortunately we do have to think about concurrency. And this is one of the particular models you use. It's sort of a pipeline model.
Mm-hmm. The regulators weren't really happy unless we sort of did a bit of this.
Yeah, we kind of have to have DR and HA. They don't just sign us off and we can't do business if we don't have this sort of thing. So this is kind of the Cedar model we talked about earlier. This was actually the architecture we ran for quite a decent period of time. So stuff coming in off the net, we've got messages. This is all fairly asynchronous, which is a fairly common design patterns for high-performance, high-throughput systems. So messages coming in off the network, these are just bytes. Pump them off to an HA thing synchronously, off to a DR site asynchronously. We need to switch the machine on and off again, so we whack these bytes out to a journal. In the case that we need to restart the machine, shuts down. If it's a nice clean shutdown, you can probably write it off to a snapshot somewhere. But if it fails in the middle of the day, you bring it back up and it just starts replaying the messages back into the system. We want to turn the message we've got off the wire into something useful and some sort of object that we can use to invoke our business logic. We've got our actual business logic. This is the bit where we've just been talking about. This is where all the domain logic sits. This is your nice single-threaded, very efficient piece of code. You've obviously got business logic's going to do something. It's going to tell something about some of the work it's done, send out some events. So we've got to turn that message back into a bunch of bytes again and punt it back out in the network off to another system to say, off to our clients to say, your order's been matched or something like that. This is a pipeline process, and it's quite an easy way to get decent throughput. You imagine you can have basically a thread at every one of these stages, and you'll be passing events in queues throughout the system. Just a show of hands. Imagine you've got a thread here and a thread here. You've got a producer and a consumer, and a queue in between them. How many threads are writing to the queue? 1? Show of hands. 2. The 2s have it. And this is where we get into a very interesting case. You've got 2 threads writing to the same shared piece of memory. As we mentioned earlier, that's something that can cause us some problems.
Yeah. And the 1P1C case is the easiest one to deal with. If you've got multiple threads writing to that queue and multiple threads taking off that queue, you just got a huge contention problem. So we spent a lot of time looking at queues. Queues are fundamentally either implemented as a linked list or array backed. Linked lists are kind of great in that they can grow to whatever size we want. Interesting thing we've discovered with queues is queues are always either full or empty. There's never anything in between. Your system's either running really smooth and they're just consumed straight away. You've got a contention point then. And what you find is that the head and the tail are pointing to the same node quite often. And if you've got a linked list, you're trying to track its size. So how do you keep all of these different variables up to date without any contention issues between them? This is where I kind of argue a queue has actually got conflated concerns. There's a number of concerns going on inside this one class, and that causes a problem. It's actually at its worst. So imagine if you only have 2 nodes in that. Look how many hot links that have to be patched concurrently for that going on. So you can wrap a great big lock around the whole thing, but we know what locks do, or we can use a whole bunch of CAS operations to do that. That's a lot of CAS operations. CAS is kind of interesting in that it doesn't leave user space, but what it does do is force the CPU to actually lock the pipeline so that no things can go out of order. So your compiler can't do nice reordering under a CAS instruction whilst it's happening. So it stays in user space and it's nice and fast, but it does force some ordering issues. Well, we can go to an array-backed one, so we're not patching all of those links. The interesting thing with the array-backed one is that, again, whenever the queue is either full or empty, you've got the head and tail pointers right next to each other, and they typically end up in the same cache line, as we're showing here. Now, when they're in the same cache line, they might as well be the same variable. You've now got the contention problem all over again. And most of the systems you'll see where people are talking about doing actors or whatever, you stick queues between all of these things, so queues end up becoming an issue. There's techniques you can use to get around them. For example, I wrote a 1P1C, so you got one producer, one consumer to a queue, using just memory barriers for that to work. The standard built-in JDK queue could get to about 4 million operations per second on my laptop. By going to just memory barriers and very carefully writing this queue, I could get sort of 17 to 20 million a second, but still started causing contention points after a while. And one of the fundamental problems, going back to the previous design, is that when you've got a pipeline process, if any part of the pipeline stalls, everything stalls. And someone used the analogy earlier on systems thinking, it was Dan, around someone carrying buckets of water along a line. Wouldn't it be great if everything else could continue without that problem happening? So there was a kind of perfect storm of number of ideas we were looking at. We wanted to overcome the problem that if something stalls, we can make progress in the rest of the system. How do we make things predictable? How do we get around the issues of queues? How do we actually store some data that we're replicating in case we get a failure replicating that can be resent again? And we drove a design based upon all of these needs, and we came out with a new design to this sort of system.
So this is our disruptor pattern. One of the key structures, we have a kind of a running joke at LMAX, is that every problem in computer science can be solved with another layer of indirection and a ring buffer. It's what gives us the ability. The reason we picked a ring buffer was never for performance. We weren't thinking about performance at the time we chose this data structure. It was a key thing because what we wanted to be able to do is have these messages flow into memory. And if something like a replication pair, as Martin talked about, happened to go away and come back in again, every one of these messages is sequenced by the ring buffer, and it's been sent out with that sequence ID. And if the replication pair comes back in and a bunch of messages have flown past it while it was down, it can just maintain a high watermark, see an event that it's way ahead of where it expects, sends back a NAC, and over on the main processing node, it can just rewind back to the ring buffer and start sending things out again. So the key design decision was actually for a functional reason rather than a performance or non-functional reason.
So we can simply just insert things into the ring buffer. So what we have is we've separated out a number of concerns. Is the ring buffer itself, if you're going to produce to a ring buffer, you want to claim a slot. So let's separate that concern out completely. And we do that with a chaos operation. So I want to claim a slot. The receiver can claim slot 103. If there's not multiple things writing into the ring buffer, and actually sometimes it is actually the best way to go, and we'll cover some of that in a second, you don't even need a chaos operation. You can just use a memory barrier. So Java volatile being one example of once you write that, you get a memory barrier at that stage. Now, what about everything else? We have the need to replicate, we have the need to journal, we get the need to unmarshal. They're not dependent on each other. We just need to know that at any given point in time, all of these operations have happened before we advance into doing the business logic. Well, how can we do that? The ring buffer's at 103. Things are reading that for its happening. And see, remember, they don't need locks here. They can just read something that's had a memory barrier applied to it, and they can then start working on that. So it's 103, they can start working themselves. And where we separate the concern out is the counter that they're at belongs to themselves, not to the queue or the ring buffer. So I've got a replicator running at 101, I have a journaler running at 101, and I have an unmarshaller running at 102. The business logic can now progress with 101, or anything up to that point. Now, if one of these things were to stall, the rest can still progress. And then what we tend to see in the system is if you ever get a slight stall, everything else goes as far as it can, and then that other thing catches up really fast because there's nothing else competing with it for resource at that point in time. So this really smooths out all sorts of latency blips, and just throughput is phenomenal, much better than the pipeline scenario. The beauty of it is when you come to optimization, you only need to fix the slowest thing in the system because it hides everything else. In the pipeline model, you have to go along fixing everything to get performance. If our journaler's our slowest thing, forget everything else. Just fix the journaler. It's perfect for theory of constraints and how to approach this.
One of the other nice little features of this is sort of more of an implementation detail is the way that we determine where we are is the business logic will say, I've just processed it may be processed number 90. It says, give me 91. This is going to come back and say 101. At that point, the business logic doesn't have to say wait for anymore. It can simply just make its way straight through that array, just literally indexing into the ring buffer saying, give me 91, 92, 93, and just pass very, very quickly. So we get a really nice sort of batching effect as well, and this is very important for things like the journaler and the replicator. When you've got slower I/O-based processes, they can actually take advantage of the fact that it's going to take a number of microseconds to actually write the thing to disk. By the time I come back, this is probably advanced further, especially if my load's quite high. So come back and say, oh, it's actually moved on 10 numbers. I can grab those whole 10 messages, stick them in one byte array, and chuck it straight off the disk as well.
The curve for this, rather than giving a J curve on performance for the latency, you get a bathtub. So actually sending some load through it actually makes it go faster because you get less collisions, which is completely counterintuitive. Any other collections that we've seen before, when you reach that point, you actually always slow down. We get faster up until the point we just saturate either network connection or a disk. So what's typically in there? We're also worried about garbage, because if we generate lots of garbage, we'll end up with big pauses. And there's a great expression in garbage collection, only the good die young. So you want to get things, if you want to allocate objects, make sure they stay around for a long, long time, or they die really quickly. That's the sweet spot. The sour spot for a garbage collector is things that live for a while. Just long enough to get promoted, but then have to be collected afterwards. And whenever the heap gets fragmented, you get a compaction, and the compaction is what kills you with the long pauses. And so go talk to the Zool guys or something, and they can explain all the fun and games that happens there. So what we do is we pre-allocate in the ring buffer all the buffers that are going to come off the network. We pre-allocate in that ring a whole pile of buffers, and we just use them. We copy into them. And by copying in straight away, we've got a copy cost, but there's no GC later. And we just set the sequence. We also we generate bytecode ourselves for an invoker, so we don't use reflection. And this gives us a nice way to call a nice, pretty Java interface without doing anything funky by just generating a bytecode for that. So that's part of our tooling to how that works. And we just go around reusing those over and over again in the ring buffer. And we get beautiful cache locality because you put a new message into the ring buffer, the journaler reads it, writes it off the disk. It's now hot in cache, probably an L3 cache. Another core is running. It goes, oh, I need that buffer to replicate it. Oh, it's already in cache. I just read it. No conflict, straight out again. I need to unmarshal it. It's in cache. I'm going to use it. Go straight off again. And they're all writing their own variables. There's just no conflict. In all of these cases, you've got one writer of data, many consumers. So you get this just nice publish effect with no contention. How do we get data out?
So on the way out, exactly the same thing. Add a ring buffer. We have an additional thread here to marshal some of the stuff out. And then basically we have a thread running on the other side, which just looks at the minimum of the marshaller, and out it goes. It's pretty much the same model, in and out. It's really one of the other really nice things about it is we can quite clear, this is basically an entire app. We have one whole service is basically this. We have stuff coming in, stored, do some work, and out again. We can actually count the number of thread hops. We can count the number of context switches that are likely to happen and count the network hops. And that becomes really, really important when you're trying to get very predictable, very low latency, is to have a very clean and clear understanding of what the system's actually doing. This message to go in at this point and come out at this point in less than a millisecond, what are the actual steps that thing has to go through in order to get there?
Usually about this stage, someone comes up and goes, what if you overrun the ring buffer? It's usually a really good question. Two answers to that. One is we tend to be so damn fast that you can't feed data into it fast enough to actually do that. But if it is going to happen, we separate out the concern of claiming a new slot in the ring buffer. And what it does is it looks at the things that are the other side and will busy spin or yield if the things on the other side aren't going fast enough. And so you get natural back pressure occurs in the system. So you get the effect of a queue without the problems of a queue and how it works. And on the way out, very similar things for structure, just inverted.
How do you handle the problem when the front guy has overrun? I mean, I guess that was what you're saying.
Yes.
The unmarshaller is at 0 now.
Yeah.
So your mid is messed up. So
these numbers are monotonically increasing, so these are just longs that keep going off into wherever. And what we actually do is, this is always sized to be a power of 2, so we just mask the value straight in by the size of the ring buffer. So the actual numbers just increase forever. And this is really important for our reliable HA and VR scenarios, because somebody over the other side, he's actually using the same value to ensure that he's getting a completely sequential sequence of events. One of the aspects of a trading platform is very much you can't lose a message. Every single message has to go through. So you're trying to make sure that if you see any gaps, you can go back and grab that message out and replay it.
You restart every day, though.
Yeah.
Yes. Well, we also take a snapshot and we run journals from that snapshot forward, so you don't have to go back to the beginning of time. Unlike other exchanges, we're actually a 24-hour exchange, so we have to go around, but we use the window at night to restart, not for any other reason than we don't want a GC pause, so we flush down. We've actually discovered that we can run about 5 days until we get a compaction, so we don't want to see that. We run for 24 hours, restart, and avoid that case.
We're doing a little bit of experimentation with just using the system.gc in the quiet period, hoping that will do enough to do a compaction for us, but sort of yet to see whether that's going to be useful for us. But yeah, the interesting difference between us and other trading platforms is just about all other trading exchanges, the institutional ones. They throw away all their data at the end of the day. They just rely on all the trades that have happened are all sent out to the clearinghouse and they're matched later on. And they can just throw their journals away and they just start up completely empty and all the market makers come back in and reprice. We have a slightly more difficult situation that we can't do that because we're holding retail positions and because we have to be able to close out a customer if they're getting into a really bad situation. We hold their positions in our execution venue so we can very quickly go, liquidate this person's positions without having to have a separate order management system from the outside monitoring the markets and pushing that data in.
I think one of the biggest surprises from working on this type of system is because everything's journaled on the way in and everything is completely predictable. How many people have worked on a system where it's large volume and you get a bug in live and you try to recreate that bug and it's a nightmare, it's virtually impossible? We take the logs, take them back to our staging servers, run them through the staging servers and step to the point where the bug happened and we've got exact context, complete determinism, and it's really nice to fix bugs.
Yeah. We've got 2 core services that run using this model, and normally when you place an order, either via market maker, it goes through one, and if you're coming off the retail side, it goes through 2 of these services because we've got to manage the risk for retail users. But there's no hit to a database on those key order flows, but we do have a couple of services sort of sitting on the side doing some CRUD data management for us that are database oriented. And it's really annoying when there's a bug in one of those. This is so much easier to work on and debug and use because it's so much simpler. You just get the ability just to, something went wrong, replay the journal, see where we ended up at.
Yeah. And the thing is, have we done this just to be a financial exchange? Yeah, that's where we started from. But we're starting to discover this pattern works so well for so many applications. Complete segue. We needed to develop a network probe. Mike was talking about how we measure our system. We have an SLA with our market makers. And our market makers are 2 of the largest banks in the world and the largest high-frequency market maker in the world who are pumping thousands of transactions a second into our system. And they want us to honor a latency requirement. So what we've done is we hoover up promiscuously all the network traffic at the Ethernet level. It's one of the things that sort of written. So pull the Ethernet packets, reassemble TCP streams, parse out fixed messages, work out state, and work out our SLAs. We've done it using exactly the same techniques, and it runs in one box and can track all the traffic across the front of our system. So a completely different approach, a different business need for it, but exactly the same pattern worked really well.
I think very early on I mentioned that we do have a little bit of spread of data, especially around instruments. We could potentially partition our system up on the basis of we could handle one instrument in one thread and another set of instruments in another. The thing is we just don't bother because this thing is so fast. Because this can do 6 million a second, we just don't need to do that. So that's another thing that just keeps everything very, very simple and very, very compact.
Yeah. I think, who has a business problem at more than 6 million transactions a second in the world? Don't think there's very many. Usually the problem is getting data into this at that sort of rates. So how can we do that? Like one of the things is maybe unmarshalling data, taking bytes and turning them into objects, fairly expensive job, or journaling to disk. The beauty about some of this design as well is we can parallelize some of that, so throw extra threads at it. So let's say we unmarshal odd and even numbered messages coming in on separate threads. I can run 2 marshalers at the same time. Why stop at 2? Mod n. Stripe out the disk, exactly the same. Let's just do it mod n. And we can just, so up to 6 million transactions a second on a single node, and that's actually fairly old CPUs, and we run the energy-saving CPUs. We're not running the X series, fastest ones with the fastest memory we can get our hands on. So if I get my hands on a new Sandy Bridge machine next quarter, I'm sure we're going to go well over 10 million a second, very, very easily. And it's just how we feed the data.
So do you fit that whole buffer in the L3? And then you
No.
do it on the other?
No.
No, this is pretty big. In production, it's 20 million items in this ring buffer, and the biggest one on the other side is about 4 million. So the size of the ring buffers is based on our sort of requirement to be able to handle an outage on something that's consuming that data. But essentially, most of that's not used. What tends to happen, because you've got a very linear seek pattern here, this is just a big array. You're just doing a constant cycle through it. You're hoping that the CPU is going to sit there and watch you striding through it and start preloading all that data hot into cache.
Yeah.
So the important bit will be in cache, and the rest of it will be just floating out in DRAM for us somewhere. Yes?
Well, I was just going to ask back to the machine-friendly. Programming a GPU, often it's less expensive to recompute values than to go and look them up that you pre-calculate. Do you do anything like that in your code where you might have some values that you bring into the method, but instead of storing it somewhere like in a state variable, you just recalculate?
One good example is we have our customer margining service. We talked a bit about the matching engine. We do similar techniques for working out what someone's exposure is. You only take a percentage of the money you need of someone in advance, and as their position changes, you might need to get more money. It's called doing a margin call. Tick by tick, we measure that, and what we do is we take those ticks in and do it on a separate model, and we completely recalculate exactly as we don't try to cache it, we recalculate, and we can recalculate positions 7 million a second. So effectively in real time, we can margin retail customers. It's our main USP. Doing the matching engine, other people are getting very fast and getting very good at this, and they've got quite simple problems. And they tend to throw much more hardware at it than what we do. But when you actually go to more complex transactions, we find it works really well. Just recalculate.
The interesting thing about the margin call one is that's the biggest constraint to building a retail exchange, and I know apparently a number of people have tried, and that's the point where they've fallen over, being able to margin call customers with derivative products in real time. You talk to some other big financial exchanges which are working more in the institutional space, and they're really, really happy when they can do it once a day. We're doing it sort of every 5 seconds, constantly keeping track of that.
Mm-hmm. So just a bit of a quick recap. It's really about sort of knowing that hardware and knowing what to do. And it's not a huge detail. The mechanical sympathy thing, I stole it from Jackie Stewart, the racing driver. He used to say that you need mechanical sympathy to be a great racing driver. You don't need to know how to rebuild an engine, but you've got to know how one works, how the gearbox works, how the basic structure of a car works to get the best out of it. So we don't need to build chips, but we've just got to know how to drive them properly. And people are getting so far back from these things these days. It's actually worth revisiting some of the Computer Science 101. I'm constantly shocked by how many people don't know the history of this subject and stuff. A lot of what we're doing is not new. It's been around a long, long time. Like our reliable messaging is actually just a play on the design that was in VMS for some of its clustering. This is all good, tried and tested stuff that's been around a while. All we're doing is assembling it in sort of modern ways.
Yeah. There's another point of that. We're talking about existing patterns and existing technology. When we were showing that same diagram to one of our partners, who's they're at the high end of performance stuff as well, they just looked and went, "That's just a network card," and it is. It just works exactly the same way as a high-speed network card does, but it's in an application. So these models aren't new. They're reasonably simple. They're reasonably straightforward. And it's just a case of understanding what's gone before and trying to reapply it, in a nice, clean way that works for you.
Yeah. We're not afraid of concurrency. In fact, we love it. It's a really fun topic. But the important thing is if you ever do concurrency, do it on a very well-bounded domain problem. And that's why the infrastructure is a good place. Trying to do concurrency in a business model is far too hard and far too easy to get wrong. So that's why we like to run the business logic just on a single thread. Push all the concurrency down in your infrastructure, make it really, really fast, and then just have a simple business model that sits on top of that. If you do that, you get that stuff that we all dream about. It's so easy to test it. It's so easy to write code against it. You actually just write a pure domain-driven design model on top of that and just pump lots and lots of data into it really, really fast. So I'm going to kind of stop at that stage and hand over for a bit of Q&A. But also plugging, we're recruiting.